Let's put everything together that we've learned about parent functions and transformations to graph some more complicated functions. Now, just a heads up, it's really helpful if you have a set of colored pencils or maybe some different colored highlighters to construct these graphs. Example 3, using transformations, graph the functions following the steps provided in class. So what we're going to do is start with our parent function. So as we've done in our previous examples, let's identify the parent function for this graph. Hopefully you can determine the parent function is the absolute value of x. So I'm actually going to construct the graph of the absolute value of x. We did this in the very first video or the very first subsection of this set of notes. So where are these points coming from? These are the same points that we used from the t-chart at the very beginning of this section. So I'm just repeating that graph here. Now, if you graph that in pencil, you may want to highlight it with a specific color or just go ahead and do that in a specific color. Now, I'm going to switch colors and take care of the next transformation. Notice we've got some operations in our absolute value. We're multiplying by 2, adding 3, subtracting 1. Let's talk about what happens when we multiply a function by 2. In this case, if we multiply just our parent function by 2, we're going to work our way up to that more complicated function. This is going to be a stretch by a factor of 2. So to actually execute this, and pay attention here, this is one of the harder transformations or non-uniform transformations, I'll say. What we're going to do is multiply each y value by 2. So let's come over here and look at the point that we've graphed at 2, 2. So looking at this point right here, the y value there is 2. I'm going to multiply that by 2 to get 4. So I'm doubling the y value, but I'm keeping the x value the same. Notice the x value here is the same, but my y value has now doubled. Okay, let's do that to the next point. The next point on the graph has a y value of 1. 1 times 2 is 2. So the new y value there is going to be 2. If I look at the point at the origin, its y value is 0, and 0 times 2 is 0. So it's not moving, it's not going anywhere. Looking at this point, the y value here is 1. If I double that, it's going to stretch that up to 2. And this last point, which has a y value of 2, if I double that, that gives me 4. So I'm going to go ahead and construct another absolute value function. Notice it's still a v, right? It has the same nature as the parent function. It just happens to be twice as tall. So this is a vertical stretch. Now we have 2 other transformations in this graph. Let me get a different color here. We have 2 other transformations in this graph, the +3 and the -1. The +3, let's start with the -1. That's the easier one. Since it's outside the function, that's a vertical transformation. This guy is going to move the graph down 1. The operation inside the function, that's a horizontal transformation. Remember, that's the opposite of what you think it should be. This guy is going to move left 3. So we can take care of both of those transformations in one step by moving each of those red points that we just plotted left 3 and down 1. So I'm going to start with this point, this rightmost point. Ordered pair here is 2, 4. I'm going to count left 3 and down 1 and make a new point. Okay, I'm kind of leaving some breadcrumbs over here so you can see where I'm working. I'm going to take the next point on the red graph at ordered pair 1, 2. I'm going to count left 3 and down 1. Let's look at the point at the vertex. I'm moving it left 3 and down 1. Looking at this point at ordered pair -1, 2, I'm going to move it left 3 and down 1. And the last point on our red graph, left 3 and down 1. This is going to be our final transformed graph. If you're an artistic person, you like color, you may enjoy these graphs. Maybe not though, right? So 2 times the absolute value of x plus 3 minus 1. I have labeled the purple graph. That is our final transformation. Now remember, you can check every single step with your calculator, and you can also just verify your last step. That's what I'm going to do in this case. So I'm going to go to y equals, and I'm going to type in 2 times the absolute value. Remember, absolute value is under your math menu. I'm going to highlight number when I get to that math menu by pressing my right arrow key, and option number 1 is ABS absolute value. So the argument is x plus 3. Then I'm going to use my right arrow key to get out of absolute value bars and type in minus 1. And we can graph, and we can match that basic shape with our graph, or better yet, let's do our second table option, and we can verify every single one of our points. Notice our vertex over here is ordered pair -3, -1, and I've got ordered pair -3, -1 right here, okay? Also, another point on our graph is -2, 1, and we can see that right here. So we can check every single point on our transformed graph. So the idea is, started out with the absolute value function. It got a little bit taller, and then it moved left 3 and down 1. It has the same basic nature as the original function. It's just in a different place. Let's practice that again. Let's look at a square root function. So in this case, our parent function is the square root of x. So that was one of our 6 basic functions, and I'm going to plot the same points that we began with when we first graphed this function. 0, 0, 1, 1, and be careful, 4, 2. That is our half sideways parabola. Okay, then let's look for stretch or shrink. Since this is not multiplied by anything, it's not going to stretch or shrink, but I do have a negative outside the function. So we want to know what happens to the graph when we introduce a negative outside the function. This is going to reflect across the x-axis. So I'm going to take each of these points and find their mirror image on the other side of the x-axis. So I'm going to start with this point at 4, 2. I notice it's 2 units above the x-axis. I'm just going to reflect it to the other side of the x-axis and form its mirror image. So whereas this one was 2 units above, this one is now 2 units below. Looking at this point, it is 1 unit above the x-axis. I'm going to reflect it to the other side, and it's going to land 1 unit below the x-axis. The vertex here at the origin does not move, so we have reflected this graph across the x-axis. Finally, we will take care of the other 2 operations. The plus 3 outside the function is going to make it move up 3, and the plus 2 inside the function is going to make it go left 2. So I'm going to take each of my red points, move them up 3 and left 2. I'll start at the vertex. I'm going to count up 3 and left 2 and make a new point. I'll take this next point, up 3, left 2, and finally our last red point, up 3, left 2. Again, you can use different colors, or if you're more comfortable graphing in pencil, you can always graph it in pencil and then go back and distinguish between your curves with a highlighter. That way you can really see the difference because there's a lot of info on this graph. Or if you only have a pencil, one thing that you can do is say, I'm going to graph the first one as a dotted line. I'm going to graph the second one as a dashed line, and I'll do the third one solid. Those are also options, but somehow distinguish between your graphs so you can kind of see what you've done there. And remember, you can verify with your calculator. Let's try another example. Remember, we always start with the parent function. Who's the parent function for this example? I hope you recognize y equals x cubed. That's our cubic function, our vertical squiggle. So remember, we generated these points by making a t-chart. You can make a new t-chart if you want to, or you can memorize those particular points. Got to start with the parent function. So this establishes the basic nature of our graph, and then we will determine transformations. The first thing that we notice is our function is multiplied by a half. When we multiply a function by a constant, it's either a vertical stretch or shrink. In this case, since it's a fraction, it's going to shrink by a factor of 1/2. Now remember, how do you do that? You multiply, remember, was it x or y? Multiply y values by 1/2. So I'm going to look at each point on my graph. I'm going to start with this high point. I'm going to observe that its y value is 8. 8 times 1/2 is 4. So this point is going to shrink down to half as tall as what it used to be, right? This point here has a y value of 1. 1 times 1/2 is a half. So it's half as close to the x-axis as it was before. The origin has a y value of 0, so it's not going to move. This fella has a y value of -1. -1 times a half is -1/2, so it's shrinking towards the x-axis. And finally, our last point, which has a y value of -8. -8 times 1/2 is -4, so it shrinks toward the x-axis. The result is a graph that's just a little bit wider than the original. That's 1/2 x cubed. To finish off, there's one more operation in our function. We are subtracting 2 outside the function. Can you tell me which way it's going to go? Is it up, down, left, or right? It is down 2 units. So I'm going to take those red points and move them each down 2 units. Now look at this one. It was at the halfway mark. When I go 1 whole unit, I'm at the halfway mark. I'm going to go another whole unit. I'm still at the halfway mark. So that one's been moved down 2. The point at the origin moves down 2. Looking at the red point here, I'm going to move down 1 whole unit and another whole unit. So we're at the halfway mark. And this fella goes down 2 units as well. So the purple graph is going to be the same shape as the red graph, same size. It just has moved out, right? So I'm going to connect those dots. And that's my final curve, 1/2 x cubed minus 2. Remember, you can verify each of those final points on your calculator. Kind of working our way through our parent functions, let's practice one with a cube root. Did I just give away the parent function? I think I did. But you knew that anyway, right? Parent function here is cube root of x. That is our sideways squiggle. So if you need to refer back to the first couple of pages on your notes where we figured out these points, remember we made a t-chart. We picked out convenient values for x and calculated y. These are the 5 basic points that we came up with. That is our cube root function. Next, we will identify the transformations. Notice the negative on the outside. If we have a negative outside the function, that means we're going to reflect the original function across the x-axis. So I'm going to form the mirror image of all of those blue points across the x-axis. So if I start with this point, the mirror image of that point is on the other side of the x-axis, right? This one's 2 units away on the north side. This guy is now 2 units away on the south side. Or this point here, if I reflect to the other side, lands down here. The origin point does not move. It's its own reflection. This point reflects above the x-axis, and so does this last point here. Okay, so the result is still a squiggle. It's just been reflected. So that's the graph of negative cube root of x. Kind of looks like a little chromosome there that we graphed. We've got one last transformation to execute. That's the +4 outside the function. Remember, if the constant is outside the function, it is a vertical transformation. We're going to take our red graph up 4 units. So all of these points, 1, 2, 3, 4, move. Now remember, we're working from the red graph, the last graph that we transformed. That way, all of the transformations will be reflected in our final graph. Again, I'm leaving the breadcrumbs there so you can see what I'm doing. You don't necessarily have to do that on your notes. Okay, so draw our squiggle. Let's make sure and label it. And again, you could verify that with your calculator. Math, highlight number. No, I'm sorry. Number is for absolute value. Here, let's just do it. Y equals negative. Now, math option number 4. There it is. Cube root of x. I'm going to use my right arrow key to get out of that radical and do +4. Hit the graph button and we could verify point by point. Looks like our overall shape is good. And we could go to our table function, second table, and verify individual points. Okay, specifically that turning point there, 0, 4, that's right in the center of our graph. We did a great job. Okay, one more example. Let's throw a parabola in here. The parent function, and by the way, this graph has almost all the transformations in one. All but one particular transformation. So since we're looking at our parabola, we start by generating those 5 key points. That's where you always start when you're graphing a function. Identify the parent function and make a graph. That's the one we're going to be transforming. Now, we've got a couple of transformations. Notice we are multiplying by 3. That means it's going to stretch. And we have a negative. That means it's going to reflect. You can actually knock both of those out at the same time. So let's look at negative 3x squared. This is going to reflect across the x-axis. That's because of the negative. And it's going to stretch by a factor of 3 at the same time. So how can I knock both of those out together? I'm going to multiply the y values only, by negative 3. That will reflect and stretch at the same time. Okay, here we go. Starting with this rightmost point, I'm going to observe that its y value is 4. 4 times negative 3 is negative 12. So this point is going to keep the same x value, but the new y value is going to be negative 12. That's going to be way off our grid. 9, 10, 11, 12. Way down there. Okay? Next point won't be so bad. Let's look at the y value of our second point. The y value there is 1. 1 times negative 3 is negative 3, so it's going to land here. Vertex has a y value of 0, so it's not going anywhere. Finally here, the y value here is 1. Multiply that by negative 3 to get negative 3. And the last guy ends up with a y value of negative 12, just like the other one. I'm just going to worry about the points on the grid. Okay, if you want to draw all the way down, you certainly can. But this is the graph of negative 3x squared. It's skinnier than its parent, right? And it has reflected and opened the other way. We can also knock out the next 2 transformations together. Can you tell me what the +1 outside the function does? Is that up, down, left, or right? Hope you said up, 1. And the -2 inside the function, what do you think? Up, down, left, or right? Right, 2. So our final graph will have the basic nature of the parabola, but it will also exhibit all those transformations. So working from our red graph, we're going to move each point up 1 and right 2. So starting with this point, up 1 and right 2. Vertex goes up 1 and right 2. And up 1 and right 2. So we still have that skinny opening down parabola, but it is in a new location. So I'm going to label this. The color coding sure helps. And that completes our transformations. Now, please work hard on these transformations. We will be learning later in the course other parent functions. So we're going to add to this exponential functions, logarithmic functions. They're going to have all the same transformations that we learned today. So if you can really master recognizing, is it up, down, left, right, does it reflect across the x-axis, so forth. If you master that, it'll be a little bit easier later on. And don't forget, if you can't remember, does it go left or right, up or down, you can always verify it with your calculator. So please practice doing that.